Today, you're recording? What I want to talk about today is the average behavior, average complexity of quicksort. So it's quicksort. There's also another analysis here that I'm not going to get to, which is the BST analysis, but I will cover it later, although you could look ahead at it if you're interested. What's a BST?
Binary search tree.
Binary search tree. So we're looking at the average behavior of quicksort and binary search tree. The first thing we're going to look at is the quicksort. So just to remind you what the quicksort looks like, right? So the quicksort algorithm looks like this. This is, we want to sort an array from some index P to index R. So if P is less than R, means you have at least two elements. Then call partition, which takes an arbitrary element and places it using the partition algorithm that we talked about, and returns the index of that location, and then recursively we quicksort from P to left of that element, and then recursively again right of that element to the right side. Okay? Everybody remembers that? And of course, this is the partition algorithm. We talked about all the i's and j's, right? Where we try to find the location, and if we have two violations, we swap them, and we keep moving this I and j. And whenever I stops, that's the end of the left partition, and we just swap this, and then gives us a partition of everything less than or equal to, everything greater than this way. Okay? Any questions about it? Everybody remember that? Remember that? Remember that? All right. So that was the idea here. Okay. So now what we're going to do is we're going to use a function C of n. Give me a second here. We're going to use a function C of n to be the average number of comparisons used in quicksort. Why are we looking at comparisons? Because comparison is what in quicksort? Characteristic operations. So if we can count those characteristic operations, it's going to give us a good idea. Okay. So Cn is going to be the average number of comparisons used in quicksort. Now, let's remember what happens. If we start from an array of n elements, and our data is actually completely unexpected random data, and not in order, then we will choose, for example, the first element to be the pivot element, and then we'll try to do the partitioning, moving this I and j, and eventually wherever the I ends up, that's where the pivot goes, and then it splits, the partitions the array around the pivot. Now, if the split is equally likely to go anywhere because the element is equally likely to go anywhere, because they're random data. So an element with unsorted data, unordered data, random data, if you take one element out, the probability that it actually belongs here is 1 out of n. The probability that it belongs here is 1 out of n, 1 out of n, 1 out of n everywhere, because it's equally likely to go anywhere. So the pivot is equally likely to fall anywhere in the array, correct? If the pivot falls into its original position here, then the recursion to the left has nothing to do, and the recursion to the right has n-1 to do, right? So therefore, we can say that the average number of comparisons in that case is going to be 0 here, and then the average for the next level would be the average of n-1. So the average of n, given that the pivot goes back to its original spot, is 0 on the left side, and the average of n-1 on the right. If the pivot moves, let's say, 5 locations into position 5, then the average for that is going to be the average of n is going to be the average of n on this one level, and then it's going to be the average of 4 here, and the average of n-5 here. So wherever that pivot goes, basically it's going to split. But we know that pivot is equally likely to go anywhere. So if it goes to 0, we have 0 n-1, then we have 1 n-2, 2 n-3, etc., etc., etc. So we can use the assumption that the pivot will fall anywhere with equal probability to get this equation, or recurrence equation. This recurrence. This recurrence says that C of n, which is the average number of comparisons, is going to equal to the average number of comparisons of 0 plus Cn minus 1 plus C1n minus 2 plus C dot 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 n minus 2 1 and n minus 1 0. In fact, what I've done here with the ellipsis here is simply look at all the possible things that can happen. So C0 is the pivot goes originally to its initial spot, so I have n minus 1 on the right. Here the pivot goes into position 2, so I have 1 on the left and minus 2 on the right. What's the next one that I missed here in the ellipsis? What's the next one? C2, Cn minus 3, C3, n minus 4, etc. So what's going on is this is increasing C0, C1, C2, C3, Cn minus 2, Cn minus 1 is the maximum number. So this one is increasing by 1. As this one is increasing by 1, this one is decreasing n minus 2, n minus 3. Okay? Finally, we are going to n to 1 and then to 0. Okay? Because as you increase this way, then the right side becomes 0. So actually, it's kind of a symmetric thing. So now, what we have is we're saying the average number of comparisons on this one is simply all the possible ways that the pivot can fall at this level of the level 0. And this is all the possible things that can happen with level 1. Is that correct? Yes? Okay, and then what we're going to do is we're going to divide it by n. Why do we divide it by n? That's the average. So if basically all are the possible things that can happen, okay, so this is an average complexity of n is equal to the average complexity of this plus this, 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 but there are n possible this plus this. This is one of them. This is the second one. This is the nth one right here. The nth split is with your end up on the right-hand side. You have nothing to your right and everything to your left. So there are n. Notice that this is two things here. This goes with this. 0 and 1. 0 and minus 1. 1 and minus 2. So there are n ways that we can place that pivot. So there are n pairs of left-rights, left-rights, left-rights. If we divide it by n, that will give me the average level at level 1. Plus n plus 1. What's plus n plus 1?
Number of comparisons.
Actual work. Those are the actual cost of partition. So roughly speaking, it's going to be, I have n plus 1. You can use n plus 1. It's basically the same idea. Okay, does everybody understand this setup? Any questions on that? How we did it? Make sense? He's very smart. All right.
So,
Yep.
is n plus 1 is like an n comparison at the loop and then one final comparison of the n of the partition?
Say it one more time, please.
So I'm saying the overhead cost for level 1 is n plus 1. Is that like,
Not overhead, the actual, right?
yeah, actually?
So that's the partition cost, basically, is what we're saying. So that's the actual cost, and everything else is a recurrence. So what we can do is we can use summation notation, because this is like a pattern, right? It's a pattern. So it's a recurrence, but it's kind of a nasty recurrence, because it's got a lot of terms. Normally we used to recurrence like T of n is equal to T of, another T, T of n over 2, 3 times, maybe another one here. But this one has n recurrences, and they're doubled in pairs. So it makes it a little bit extra scary looking, but let's see if we can handle it. There are a lot of analysis of average behavior of quicksort. And from all the ones that I've studied in my career, I've seen that this one, I think, is the simplest one, believe it or not. Absolutely the simplest. The other ones are really get much more, but it gives you the good result. So, because this is a pattern, what we're going to do is we're simply going to write a pattern just like this. So C of n is going to be, so this is n plus 1, that's the same thing here. This is divided by n is here. So this summation is simply taking each of these, plus this, plus this, plus this. And so what we're going to do is we're going to let I go from 0 to n minus 1. And as I is increasing, it's going to be C0, C1, C0, C1, C2, Cn minus 2, Cn minus 1. So this is going to be increasing up to n minus 1. In pairs, this one is going to be decreasing from n minus 1, starting at n minus 1, minus 0, then n minus 2, n minus 3, so that this is going to give us this. But we can also see that if you look at this, C0 here, the average number of comparisons of C0, which is 0, is the same thing as this C0 here. And Cn minus 1, the stuff on the left, when the pivot goes to the right, I thought it was a cold air coming from here. Quite interesting. There's a door to the outside, cold. Oh, it's coming from there. Let's pause the recording for a minute. Seeing C0 and C0 here, and then we're seeing Cn minus 1 here and here. We see that each of them is occurring twice, and even though these are pairs and pairs and pairs, there's just addition here. So we can remove all the parentheses actually, right? And recognize the fact that this is a symmetric one, so basically what we have is we basically have 2 times I from 0 to n minus 1 of Ci, so this gives me C0 twice, tick, tick, and it gives me Cn minus 1 twice, again here, and everything in between. So we have a balancing. So that's a symmetry. So we need to solve, so the recurrence still is complicated because it has this large summation of recurrences, but at least we took half of it away. So that makes it better. So what we're going to do is we're going to try to do something with this summation the way we have it, and we're going to multiply both sides by n. N is a large positive number. So here we had initially, before we had n, is this Cn, so now it's NCn. And now we'll do the same thing here, we'll multiply this by n. So when we multiply by n, we have n times Cn times 2 times this plus n times n plus 1. Okay? And then we'll also write, what's this? What does that do for us? Why do we do this? What is this called? We've done this before. What is this called? Repeated substitution, right? So what we did was we basically solved it for n minus 1. So again, substituting n minus 1 for n, we get this, we get this, we get this, we get this. So we have equation 1 and equation 2. So now we're going to try to get some kind of a difference. So what we're going to do is we're going to subtract equation 2 from equation 1. So equation 2 is being subtracted from equation 1. So that means we're going to subtract this one minus this one, and this one minus this one. We're going to try to get a difference. So that you can see how that's working. So it's NCn minus n minus 1 times Cn minus 1. That's the 2 minus 1. And then this one minus this one. So what do we have? We have NCn minus n minus 1 Cn minus 1. That gives us here. But here we can see something has been simplified, and we have taken away a lot of terms here. So we have n times n plus 1 minus n minus 1 times n. And what did we do here? We recognize the fact that this goes from 0 to n minus 1. This goes from 0 to n minus 2. So what do we have left? Which term remains? For which one? This left or right side? Left. For the index equal to? Which index remained?
Minus 2 to minus 1.
This is going from 0 to n minus 1.
N minus 1.
So n minus 2 comes before n minus 1, so n minus 1 remains. So that means this, when I is I minus 1, n minus 1, this term exists, but this one doesn't have it, so the subtraction doesn't take it away. So n minus 1, this is going to be 2 times c of n minus 1. This is the remaining term. So I think we did a very nice job, because basically we reduced the recurrence. Instead of having a summation of them, we now have 1, 2, and only 3. So it's a little bit easier. So we can try to simplify our terms. So here we can just multiply what we have here. You can see we have n squared plus n minus n squared minus n, or plus n. So if we simplify that, we get basically 2n. So we still have this right here. And now we're going to recognize the fact that we have c of n minus 1 occurring here and also occurring here. So what we can do is we have minus n minus 1 of them, so we can add n minus 1 of them here. And then when we add the coefficients of 2 to n minus 1, we have n plus 1, c of n minus 1. Does everybody see that? You want me to do it again? Okay. So what we did here is, this is an important step. So what we have here is, this is the same. This is, okay. So now over here you have, so c of n minus 1, think of that as c of n minus 1, think of it as a quantity, something. Think of it as a telephone, okay? So I have 2 telephones, correct? Here I have minus n minus 1 telephones. So what I'm going to do is I'm going to bring these terms onto this side. So that's going to be plus n minus 1, right? Plus n minus 1 times that many telephones. So I have plus n minus 1 plus 2. So I have n minus 1 plus 2 is n plus 1 telephones. Whatever that quantity is, because that c of n minus 1 is just a quantity. Okay, so that's how I end up having this value here. This is just 2n continues, this continues here. So now, again, we've done a very nice thing, because now we have a single original Cn, okay, and now we only have a single recurrence on the other side. So the way we did it, basically, is we had a summation. We simplified the summation to half of the summation. Then we did a difference of those two to be able to get the telescope to cancel out all but one term. And then we combined the two Cn minus 1 terms to produce this setup right now. So now we want to be able to solve it. Okay, so we're going to choose, and again, it's not a trivial one, that's why I'm going through it. We're going to choose to divide both sides by n times n plus 1. Notice that here we have n as a factor. Here we have n as a factor. Here we have n plus 1 as a factor. So we're going to divide it by the common denominator of those two, which is n times n plus 1. So that's going to give us c over n plus 1 plus 2 over plus c n minus 1 over n. And that's what we get here. Okay? And now we're going to do the same thing again as we did before. And that is, we're going to take this equation and we're going to write this equation substituting n minus 1 for n. So this is going to be c of n minus 1. This is going to be n minus 1 plus 1. Same thing here. This is going to be n minus 1 directly. Okay? Everybody understand what we did here? So we have equation here, we have equation here. Now we're going to substitute c of n minus 1 over n into equation 3 with the right side of equation 4. So we have this equation is still the same. This part of the right side is still the same. But now c of n minus 1 can be substituted for this part right here. So this is going to be the substitution of the value of the right side of equation 4. So that's what we have here. So you can see it's going to be c of n over n minus 1, 2 of this plus 2 of this. And we'll substitute again. Get the pattern here now what we're doing? So we're going to substitute now for c of n minus 2. And c of n minus 2 is going to be a very similar looking thing, right? So what's that going to be? 2 over n minus 1 times c of n minus 3 over,
N minus 2.
okay, and that's what we have here. So we're seeing a pattern emerging. Now, so once you see a pattern emerging, you're like, yay, a pattern is emerging, and you try to see what the pattern is if I were to do this I number of times or some variable number of times. So if we repeat this a number of times, we can see that basically we are always continuing to get a 2 on top. Okay? And at the end we have, when we did it 3 times, we have C of n minus 3 over n minus 2. So therefore it's going to be n plus 1. This is getting reduced by 1, so it's n plus 1 and n minus 1. And this is n minus 2, but we did it 3 times. So that means this is not n minus I, it's one higher, one lower than I. So it's n minus I minus 1. N minus I minus 1 is n minus I plus 1. Does that make sense? Yeah, so you're taking, so basically the number, and this is important for detail, so the number of repetitions was equal to I, right? So now, so we can see here that this is, we can see here that this is C of n minus I, okay? But what we're seeing up here is that this is n minus 2, even though here we did how many substitutions? 3 substitutions, but this is n minus 2. 2 is 1 less than 3. So that means we need 1 less than I in general, which means I minus 1. I minus 1 goes, so it's going to be n minus I minus 1. And when we have n minus I minus 1, we have n minus I plus 1. So that's why this comes out as n minus I plus 1. But this is n minus 3 for 3 repetitions, so it's going to be n minus I for I repetitions. Make sense? Okay, so we can see that we have this pattern here. Now, we can let I equal to anything we want it to, any positive integer, right? So therefore we will choose to let I equal to n. Why? Because if I is equal to n, then C of n minus n is C of 0. And C of 0 is how many comparisons on average do you get with 0 elements? 0. So that is able to cancel out, and now we are very close to getting a solution because now we are getting close to a closed form. All we have to do is find out what the summation is. Are you with me? Okay. Okay, so now we have C over n, n plus 1, etc. What are we solving for again? C of n. Okay, remember, C of n is the average number of comparisons. So what we're going to do at this point, we can pull a 2 out because a 2 is going to occur in every single term on the right-hand side. So we have C of n over n plus 1 is equal to 2 removed from here, right? So you can see that what we have here is, so I don't know what n is, but if n is, for example, 10, this is going to be 2 over 11, 2 over 10, plus 2 over 9. So you can see it's some kind of a sequence. What kind of a sequence is it?
Arithmetic progression. Arithmetic progression.
Okay, and what type of a series do we call it? So notice that we're going to go, so the top is the same. So it's like 1/2, 1/3, 1/4, 1/5, up to 1 plus 1. It looks like a harmonic progression. Harmonic progression. Okay? Because there's no ratio, so it's not a geometric progression. Harmonic progression. So you can think of it as 1 over 1, 1 over 2, 1 over 3, all the way to the 1 over 1 plus 1. So we have a harmonic progression. So now, what we're going to do is we're going to multiply by the denominator of the Cn, which is n plus 1, and we get Cn is equal to 2 times n plus 1 times this harmonic progression. But we know the harmonic progression can be written as h of n plus 1 in notational standpoint. And we also found by using integrals that the harmonic sequence has a lower and upper bound which is proportional to log n. So therefore, we're going to say that C of n is now approximately 2 times n plus 1 times the log of n. Now, ln(n) is log with a natural base. If we convert this to lg, which is log base 2, which a lot of people like to do, this comes out to a complexity approximately 1.38 n lgn. 1.38 n lgn. Okay? So we have shown that the average, which is critical, average complexity of quicksort is n log n, which is of course proportional to constant n lgn, right? So this is a very important result. Very important result. Let's think about what this result means. It means that if you take random data in an array for quicksorting, random data, okay, and you quicksort it, the number of comparisons is going to be approximately 1.38 times n lgn. Now let's put that into perspective. What's the worst complexity for quicksort? N squared. So the worst case. And we know when that happens, right? That happens if the data is already sorted. So that's going to be the worst case. But again, and if the data is sorted, we'll talk about that in a second. That's bad because it's quadratic and it's going to be n squared. This is the case where the data is random. So the pivot is equally likely to go anywhere. Okay, so let's think about the case where the array is exactly perfectly suited to have the best case. So the best case, what we're going to do is we're going to have one element, the pivot is going to go exactly into the middle, split it into two pieces, which are going to go, those pivots are going to go exactly in the middle, which are going to give us 4 pieces, and those pivots are going in the middle. How many comparisons are we going to have? Well, let's find out. Do you know? Let's look at an example array. What's a number? What's a good number to use this kind of an array that always splits in 2 to the k minus 1? So we're going to use an array of 2 to the k minus 1, right? Because that always, if we pull one element out, we have 2 to the k minus 1 left on either side. Because that splits into 2 to the k minus 1. And this splits to 2 to the k minus 1. And the middle element is 1. So that's, and this is the pivot. So in the case of 7 elements, let's see what's going to happen. So what is typically the number of comparisons that we do? Well, we're going to have 7 elements here, right? So how many elements are we going to have? So again, it's going to be a perfect pivot, so that means the element here is going to go into position number 4 out of 7, right? So if this is 1, 2, 3, 4, 5, 6, 7, this pivot is here, but it's going to end up here. Right? So we're going to need, roughly speaking, what's the complexity of the partition? Partition is, what's the complexity of partition? No, I mean, I'm talking about from the standpoint of complexity, not a count. What?
Log n.
No. N. Yeah, partition is n, because it's got to go through every element, so n. So roughly speaking, we're going to use about 7 comparisons. Right? Now, then we're going to split it exactly into 2 levels, and those 2 levels are going to get how many comparisons? 3 and 3, right? Which is 6, which is still order of n, which is 7. So we're going to say roughly 7. We're overestimating. And then that's going to split us into what? 1 and 1. So how many levels until we get to unity? Right? First split is going to take us from 7. First split is going to take us to 3. Okay, into unity. So really, the original one here, we do a comparison, then we do split, then we do a comparison, then we do a split, then we do a comparison. So we basically have effectively n times 3 times. But why 3 times? Well, this is approximately equal to, n is equal to 2 to the k, and that's Lg of n times n. So this is theta n, and the number of times it happens here is Lg of n. So that means that the best number of comparisons, roughly speaking, is n Lgn. Do you understand what I'm saying here? So the best case, absolute best case you can have, which is very unlikely statistically, has n Lgn number of comparisons. But the average case, where you just throw random data all mixed up into this thing, has 1.38. What do you think of that? Do you think is that a surprising result, or is that like expected? It's really surprising, because we know that the pivot is equally likely to go anywhere. It could go here, could go here, could go anywhere. What are the chances it's going to go in the middle? Very small. If you have an array with 1,000 elements, what's the probability that this thing is going to go into position 500? It's not very big. In fact, it's 1 out of 1,000, roughly. But the probability that it's going to go here is equally unlikely, and when it's around the pivot, it still gives you a pretty good result, as we saw for our analysis, the 1090 analysis, bad good analysis, and this is an analysis of average random data. So the average random data, the number of comparisons, is only 38% more than the worst case, than the best case. So if you think about an array, let's say an array let's say we have k is equal to 11. Let's say k is equal to 10. So if k is equal to 10, array size is what? No, not a million. It's just going to be 1,023, or roughly 1,024, right? Okay, so the number of comparisons in the very best case for this array is going to be what? What's k LGN? What's n LGN? If k is equal to 10, what's the best number of comparisons? It's going to be n times LGN. What's LG of 1024? It's going to be 10. So that's going to be 10 times 1,024, which is 10,240. Okay? But a random array, completely random array, is only going to be 1.38 times that. So it's going to be 38% of 10,000. So roughly speaking, 3,800. 3,800 more. Just about a third more than the best case. So it's a remarkable, exciting result, telling us that quicksort performs remarkably well on average. We also have to keep in mind that quicksort performs remarkably bad on the worst case. So now we have to think about how do we prevent that worst case from happening. Any ideas? So we want to now change the worst case to the best case. You see, quicksort is the implementation of choice for many standard sorting algorithms, like in C++ or in Java or in C#. They use that algorithm. But they can't use it the way we used it, because if they use it and they expected the data to be random, that's a bad idea. Because if you have an array of 1 million elements and all of a sudden you decide to use the standard sort and your data happens to be sorted, all of a sudden this sort is not finishing because it needs 1 trillion operations, which is 1 million squared. So how are they going? What's a way that we can modify quicksort so that we avoid the worst case?
Switch to another sorting algorithm when the worst case arises.
But we don't know when the worst case arises. Well, we do. We can check in linear time. But we want to, it's a very good answer that you have. But it's not the answer I'm looking for. I want to modify the way we implement quicksort so that when the worst case is happening, we don't, without us even knowing it, it's going to still be extremely efficient. Let's say the worst case has happened. So what does that mean about my data? Okay, so where do we want the pivot to go? In the best case, the middle. So where should I select the pivot from? So now, so what I'm going to do is, rather than taking this as the pivot, which gives me the worst case, I could go here, but again, I could make up another worst case that basically have the weird number so that you don't want to pick the middle. So what we were going to do is, it's also going to go kind of a bad way. So what we're going to do is, rather than choosing the pivot here, or here, or here, we're going to look at this element, look at this element, and look at this element, and compare them, and pick the one that has the middle value. If this is, so if it's ascending order, then the middle value will be here, then take it and switch it here, run the algorithm. So what is the cost of doing that per iteration? What is the complexity of doing that per iteration? In theta. Per iteration. Theta 1. Because it's basically read, read, read. If you have a billion elements, read, read, read. 10 elements, read, read, read. It's not a function of the n, right? So it's theta 1. So you read, 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 compare, compare. That's it. So you do 5 operations. And that immediately will make the worst case turn into the best case. So it's a very simple fix. It's a very simple fix. Okay. All right. Any other questions or comments about this? So this is our analysis. So this shows the average behavior of quicksort, which is very, very useful for us. Okay. Any questions or comments on that? Everybody good? Okay. So now I'm going to switch and I'm going to go into a different type of algorithm. It's also going to be a sorting algorithm, and some of you may be familiar with it. Some of you may not be familiar with it, but we'll. Okay. So this is going to be, we're going to be looking at a data structure called a heap. We're going to look at some heap algorithms, and we're going to also look at heap sort. Okay. This is a link which I just checked it out recently, and it still has all the nice code on it, but they don't have the visual, so I was going to run some visual stuff. And they used to have some very nice applets, but they got rid of their applets. They still have the code for all the different algorithms. All right. So what we're going to do is we're going to talk about, number one, what is a heap, some heap algorithms, including heap sort, including priority queue, which is another type of heap-based algorithm, typical implementation. So first of all, let's talk about what a heap is. A heap is two things required for a tree to be a heap. So this is a tree. What kind of tree? It looks like a binary tree. Okay. In order for a heap to be a heap, it has to be a complete binary tree. Complete. So complete is a word that's important for us to understand what it means. So if you look at this tree, is it full?
No.
It's not full. Why not? Missing 7 nodes on the bottom. It would need to have 7 more to be full, or lose this one, and then you're still full. Okay, but it's not a full tree. But we can say it is balanced. We talk about what balance means. What does balance mean? Balance means that the tree is not necessarily, if it's full, it's balanced. But it can be balanced if it's only missing some nodes on one bottom level, only on the bottom level. So therefore, if it's balanced, this is balanced, but I can also add here another node, and here 2 nodes. It's still balanced because it's only missing nodes on one level. Every other level is full. So a balanced tree is either full or every level but the last one is full. Does that make sense? So that's full. So this tree is full, but that is not, it doesn't define the word we need, which is complete. So a complete tree is a full tree so that if it's balanced, it's only missing the rightmost nodes on the bottom level. So a tree, to be complete, must be balanced, but the missing nodes must only occur at the right end of the bottom level. So for example, if I wanted to maintain a complete tree and add one more node, how many places can I add one node right now to this tree and keep it complete? I'd have to add it to which node? No. I'd have to add it to here, because then I would have the leftmost nodes, two of them would be here, and then I would have some empties to the right. The empties have to be to the right. If I added something here, then I would have a missing one here. I can't have any missing ones. So all the nodes on the bottom level, if it's not full, must be left filled. So there's only one place to add here to make it complete. And if you added this one, then you add here, then you add here, then you add here, 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 and here. Does that make sense? And if you fill 7 more nodes, the next one to be added would go where? Left of 7. Okay, that defines a complete binary tree. Okay, that defines a complete binary tree, but it doesn't define a heap. A heap requires a complete binary tree, but it requires also some other condition. And that condition is that a heap must be a complete binary tree, but it also must have sort of greater than or less than invariant. For example, if you look at this 23, how does it relate to its children? It's greater. Okay, let's look at the 9. How does it relate to its children? Also greater. Also greater, okay? How about the 11? Also. So therefore we would say it has a greater than, and that's called a max invariant. So this is called a max heap, because we have a complete shape, so completeness is a shape, but we also have the max invariant. So this is a max heap. So therefore we have this invariant, the max invariant, greater. So each node is greater than either child. Notice that here, the smaller child is a 9, and the greater child is an 11, okay? And here we have the greater child is an 8, and the smaller child is a 6. So the children don't have to be left or right of the parent as long as they're less than. Notice the lesser child is to the left, but here the lesser child is to the right. So the heap is having this max or min invariant, but it doesn't care which way the children go, as long as they are following the invariant. Okay. So, now this max heap is an example which is going to be useful for sorting. And the reason it's useful for sorting is because if I wanted to sort this heap, then I would have access to one very important value. Which value is most important in that heap right now? The root. And because the root we know is what? The root is the max, so therefore if I were to sort this, I would put this in the last position, because it would be the final one, it's the maximum. But the problem is if I took this thing out and put it someplace else, then I would ruin my heap. So how could I fix my heap? Well, let's say I get rid of this node, but now I'm missing a root, so I have to put a new root in there and keep it complete. So the only thing I could do is I could only use this one and put it in the place here, but then you would have a 7. Right? You'd have a 7 in the root position. Now, you'd have a 7 in the root position. Now, I'm going to call this little baby tree a subtree, and I'm going to call this one the right subtree, and this is the left subtree. So when that 7 node is placed in place of the missing 23, I have a complete binary tree, but I have a violation of the max invariant. So, what I do have is I have the left subtree is a heap, and the right subtree is also a heap. So therefore, what I'm going to do is I need to find a place to put that 7. And if the 7 is here, what is a perfect replacement for the 7? 11, because 11 is the maximum of this subheap and this subheap, but it's bigger than the 9, so the 11 goes here, and once the 11 goes here, this now becomes a nice piece of a heap, and the 7 is good here, it's not good here, so the 7 will swap with the 10. Once we do that, we have fixed the heap. What was the complexity of the fixing of the heap once we put the small number in the top? log 2n, log n. Why? Because the complete tree has a proportional height to log n. Because it's basically a complete tree is a balanced tree. Well, yes, a complete tree is a balanced tree. And it's only a few nodes away from being full. So therefore its height cannot grow crazily. It has to grow very much, like a tree, like a full tree. So therefore, the number of swap downs to correct this error was only proportional to log of the number of nodes. So it's very fast. Good. All right, so this shows you here that basically this is the same heap, except what I've done here is I simply, into these boxes, I put numbers. And these numbers are simply numbering the nodes in row order. So it's 1, 2, 3, 4, 5, 6, 7, 8. This would be 9, 10, 11, 12, 13, 14, 15. This would be 16. And if you look at these numbers, they should show you a little bit of an interesting pattern. And that is, if you look at this node number 4, the index of its left child is 8, and the index of its right child would be 9. How do I get from 4 to 8? Okay, how about this 2? Its left child is index
4.
and its right child is? So how do I get to the right child? Double it plus 1. Does this always work? Well, double it, double plus 1. Double it, double plus 1. It's not a proof, but it's correct. Right? It's a proof. Why are you going to do a proof like that? Okay. So, so the bottom line is we see a very nice pattern. You can see over here, this is 9, this is 10. 2 times 5, plus 1, 11. 2 times 6, 12. Plus 1 is 13. 2 times 7, 14. 15, 16, 17. It works. Now, so you can see, so this is what this is showing you. This is showing you that it works. Now, what about going, so I can compute the index of a node going downward to a child. What's my left child? My left child is my index times 2 squared. Right? So I can very quickly compute how to get to. How do I get to the right child, to the left child of my right child?
Plus 1. 2n plus 1, 4 to 5.
You understand what I'm doing, right? So you have to get a calculation. Makes sense, right? All right. So this is showing you this way. Now, if I want to go backward and find out who my parent is, certainly dividing 8 by 2 gives me 4, 4 by 2 gives me 2, 2 by 2 gives me 1, 6 by 2 gives me 3, but 3 by 2? How do I get that one? And 5 by 2, how does that give me? So 5 divided by 2, so what am I going to do in this case?
Plus 1.
Floor function. So I need an integer. I will just basically truncate it, use the floor function. So 5 divided by 2, 2.5, 2. 7 divided by 2, 3.53. Okay, this guy is 9. 9 divided by 2, 4.5, 4. So I can now compute my parent and my grandparent if I want to, and my child and my grandchild, etc., etc., etc. And this is the way we do it. We do this by the floor function here. Now, the other thing I want us to be able to compute, and this is very, very important for the next thing that I'm going to present, is we want to be able to... Now, let me ask you this. Which node, give me a node key value or node index number, which is a parent. Give me an index of a node which is a parent.
4.
Yes, 4 is a parent. How about another one? 2. How about another one?
3.
Another one?
1.
Any other ones?
8.
8 is not a parent because it has only external nodes, so it doesn't have any children. So, any other parents? These guys are not parents. Why not? Because they're what?
Child.
What do we call these kind of nodes?
Leaf node.
These are leaf nodes. Leaf nodes. So leaf, 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 leaf. So if you're a leaf, you're not a parent. If you're not a leaf, you're a parent. Okay. So what I want you to do is tell me how many nodes are in this tree.
8.
You have to look at this number here. Of course, it's a good idea to check, make sure this is not 0, otherwise you're going to make a mistake. So there are 8 nodes. So now what I want you to do is I want you to not look at the notes, at the slides, and tell me what is the index of the parent that has the highest index.
9/2.
So that would be?
4.
Okay, so if you take the number of nodes in the heap and you divide it by 2 using floor function, then you will get the index of the parent with the maximum index. Notice that parent, 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 no, 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 no. So the maximum index parent is 4, because the size of the heap, 8, divided by 2 floor, is going to be 4. So that's important for us also. Okay, so now we're going to max heapify, which is that's what we talked about before. This is the process of turning the heap back into a heap. And so basically, at this point, node number 2 is a violation, right? So node number 2 is a violation, but each subheap child is a max heap. So that means this is a violation, but the right subheap is okay. That's a heap, and this one, is that a heap? Is it? Think about it. Well, in order for it to be a heap, it's got to be complete and the invariant. So is this thing complete?
No.
Yes. This is complete. It's a root and a left child. So it's complete. Right? So we can swap the 8 with the 3. Why 8, not 6? Because 6 can't be a parent to the 8, but 8 can be a parent to the 6. So we swap it with a larger sibling. How about now, good or bad? Because we swapped it this way. Is it good or bad? Still a violation, right? So what are we going to do?
7.
Okay, so swap the 3 and the 7, we get this. Okay. All right, now, this is showing you that, in fact, because of the properties that we talked about in terms of being complete, and in terms of the fact that giving an index 1 or 2 or 3 or 4, we can compute the left child, right child location. Given an index, we can compute the parent location. We actually can take this tree structure and really superimpose it into an array location, where this index becomes the logical 1 position in the array, 2 becomes this, 3, 4, 5, 6, 7, 8. The 3 becomes the 8, which as you can see over here. So what happens is we go in row order, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15, etc., etc., etc. So basically what we've done is made an array out of the heap. Or more properly said, we've made the heap out of an array. Because in fact, because we can compute this tree traversal using indexing, which is super fast and does not take any memory, that means that heaps are normally always implemented as arrays. And that will tell you a little bit about why we have to have this complete business. How many nodes are here starting from 1?
8.
8. Okay, so if we had 9, 9 would go here. It would also go right here. But if we skip this one and we made the 9th node here, then that would, from the array perspective, that would be expected to occur at the 10th index, but the 9th index was invalid, empty. So you can see what's happening here. So if you had a balanced tree which was not complete, then you would have holes in the array, and you would know they're holes. So that's why the tree has to be complete, because it has to be able to map to a linear array. So now you can see the mapping. So if I hid this from you and I said, okay, give me the value of the left child. This is 2, so that's going to be 4. And the right child, that's going to be 5. Give me the parent of 10 without looking. Well, 1, 2, 3, 4, 5, 6, 7. 7 divided by 2 is 3.5. Floor is 3. That's the parent. Okay, so we can now. So what we're going to do is we're going to look at a couple of algorithms that have to do with this. And the first one is going to be the max heapify algorithm. So given an array, so now that we understand that we can navigate through a heap by indexing an array, we're going to given an array A and an index I, we assume a binary tree is rooted at I are max heaps, but AI may pose a violation. So we want to look at the complexity of the max heapify. So index I, we assume that the binary tree rooted at I are max heaps, but AI may pose a violation. So the max heap. So we're going to take a look over here. So this is going to be the process of building a heap. So first of all, take a look at this thing. Does this thing look like a heap? A max heap or a min heap? Is it one of those? The answer is no. It's not a min heap or a max heap, and the reason for that is because if I look here, it looks maybe it's a min heap because this is bigger, but this is smaller, so forget about it. So this is nothing. But the shape is complete. So we like that. It's complete. Okay. So now what we're going to do is we're going to use this idea to max heapify. So we assume that a heap, the subheaps are proper heaps, but we may have a violation at I. So what we're going to do is we're going to compute the index of the maximum parent. What is the maximum index of a parent? 2. No?
19.
No, I don't want the key value. I want the index from the array standpoint. No.
Index is 2, right?
The answer is 4. Why? Explain to us why 4.
N by 2. Index.
So n is 8. 8 size, right? So 8 divided by 2 is 4. 1, 2, 3, 4. That's the maximum parent. Okay, so listen very carefully. If this is the maximum parent, that means how many children might this node have? 1, but it might have 2. Where's Connor here today? Still, I think, enjoying the leaves. Okay, she went to look at the nice trees. I think it's very cold up there. Do you know when she's coming back?
Yeah, I
Today's-
guess
I think
by
today's
tomorrow.
Tomorrow or today?
I think today or tomorrow.
Okay. All right, so basically, this one is the maximum parent because it's n over 2 index. It can have 1 or 2 children. Now, if it has 1 child or 2 children, think about it. This node is a subheap, and this node is a subheap, which is empty in this case. But notice that that this 10 by itself is a heap. Why? By definition, a single node is a heap. It could be a max heap, it could be a min heap. It's a heap because it's a single node. And by definition, an empty tree is a node, is a heap also. Why? Because there are no violations. And it's complete. Every level except for 1 is completely filled. Well, so what I'm telling you is that the 7, now I'm trying to think, we're going to try to max heapify. So we look at this blue triangle. Now it's really nice. We look at this blue triangle and we consider the value of the maximum parent equal to 4, and we try to fix the error if it exists. Is there a violation with a key being not bigger than this? No, because there's no key, so this is fine. But there's a violation here. Because for a max heap, the child cannot be bigger, so we have to do what? We have to swap the 10 or the 7. When I swap the 10 or the 7, the blue triangle will now have a 10 pointing to a 7, and the blue triangle, will that be a max heap?
Yes.
Yes.
Okay. Again, because the shape is complete. I know it sounds crazy, but it's basically a root and a left child that's complete. Okay, so now what we're going to do is we're going to go to the next smaller index parent, which is going to be index number 3. And we do the same thing, and that's going to be our brown triangle. Notice that 4, 6, and 10. So 4 is the next parent. It has 2 children. Notice that the left subtree is a heap, and the right subtree is also a heap. The question is, now we're going to go one level higher, is that a max heap? The answer is no, because 4 is not bigger than 6, it's also not bigger than 10. Because there are 2 children, I will choose the bigger of the 2 children, the biggest heap tops, to be a swap. And I will swap 10 and 4. So 10 will come up here, 4 will go down here. So now 10 will be a parent to 6 and to 4, and that means the brown triangle will now be a max heap. And now I will go up to this triangle. Remember what's on top here? 10 is on top, 7 is on the bottom. I will look at the next parent, which is parent number 2. 19, is 19 bigger than 10?
Yes.
And bigger than 6? Then this yellow or greenish triangle is also a max heap. So now I have a root which may pose a violation, but its left subtree and its right subtree are max heaps. So in order to make the whole thing, this whole big gray triangle, a max heap, all I need to do is swap down the root to where it belongs. And of course I'm going to compare 5 against 19 against 10. See, you're using your imagination. 5 against 19 against 10, and what's going to come up?
19.
And 5 is going to go down. And then I'm going to compare 5 against 6 against,
10.
and what's going to happen?
10.
10 is going to come up, 5 is going to go here. And now I'm going to compare 5 against, 7 comes back up, 5 goes down. Does that make sense? Okay, so what is this algorithm called? It's called heapify, or in this case, max heapify, because we're making a max heap. We could have also done min heapify. If we did min heapify, then we leave this one alone, we leave this one alone, we got some work to do here. 6 comes up, 19, you get the idea. Same complexity is going to be the same, right? Now, so now we're interested in building a heap. What is that? Yes? Oh, first question from you. No, second question.
What is the maximum parent? Shouldn't it be root?
No, because when I say maximum parent, I'm talking about the index, and the root is always index 1. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the max parent means that the parent that has the highest index, and the index is measured this way. 1, 2, 3, 4, 5, 6, 7, 8.
So 4th is the maximum index of a...
So 4, so you understand that if we number the nodes 1, 2, 3, 4, 5, 6, 7, 8, then node number 4, which is the 7, is a parent, and it's a parent that has the index higher than any other parent. That's what it means, okay? Okay, so that's good. That was a good question, because otherwise it's confusing. I understand that. Okay, so the question is, what is the complexity of building a heap? All right, so that's a good question. What do you think? So you're basically going through comparisons across the entire tree. A tree has n nodes, but you're going through. Notice what's going on here. When you go to this parent, the maximum parent has only two comparisons. You know, compare these two and maybe swap. We just call one comparison. We'll just, right? Because basically it's the comparison of a single parent against its children are theta 1. Because you compare the children against each other and the bigger one against you. So that's 3 operations, no matter how big the heap is. So that's theta 1 for that level. So, so what's going on is, so let's say you have a really big heap. Let's say you have, just for the sake of argument, 1,023 nodes, which could make a full tree. Doesn't matter. You can have 1,024. That gives you that extra node here. So if you have 1,024 nodes, what is the index of the highest parent?
512.
Say it. How did you know that?
N by 2.
Divided into
Well, I don't like n. Oh yeah,
102.
n by 2. Yeah, yeah.
By 2.
Yeah, oh yeah. So the maximum parent is going to be 1024 divided by 2, floor, which is 512. Because 512 513, 514, 515, 1023, 1024. That's the first one. So to heapify it, we're going to go through 512 parents. We're going to start heapifying, and then after we get higher, we have to do more. And after we get higher, we may have to go. You understand? So we have to, the higher we go, as we're heapifying, the more down we have to keep checking that there has not been a violation. Does that make sense? So the question is, what is your feeling of the complexity of the heapify process from an array of random data? What's your feeling? What do you think it might be?
Theta of n.
Theta of n, why do you say that?
Because we have to make n times comparison. From going down to up, we are going n by 2 comparison. Then we are comparing again from top to down. So
Well, we might be traversing, if you think about it, I will tell you my big O, common sense analysis. So you know what I mean by big O, right? And I'm using big O, not little o, because I'm not sure if it's smaller. I mean, I know if it's smaller or not, but I'm not giving it away right now. But the bottom line of my big O analysis is this. What is the cost of comparing the root against all the levels if the root is the smallest and it needs to come down to the bottom?
n by
Log n. Because it needs to, for every comparison, it goes down one level in the tree. And how tall is the tree? Well, the tree is going to be proportional to log n. So therefore, to move the root in the correct location, worst case is log n. And if I look at the children of the root, if they're violating, they're also going to be basically also log n minus 1. Log n minus 1. So I've demonstrated to you that the root could require n minus 1, log n comparisons. And these guys, log n minus 1, and 4 of these, log n minus 2, and 8 of these, log n minus 2. You get the idea, right? So I could make the argument that if we simply use an upper bound of log n, which is a true upper bound, we could say that every node as an upper bound could be compared log n number of times. And how many such nodes are there? N. So therefore that upper bound complexity, big O, would be what? N log n. So we certainly can make the, anybody disagree with that? That certainly is an upper bound. Now, is it an upper bound, meaning big O? Is it a little o? That means that the actual complexity is going to be lower? Or is it actually n log n proportional to that big O? I don't know. So he seems to think it's lesser. Anybody else have any idea what it might be?
It can be exactly n log n if the highest number is on the root, right?
And we want to basically look at the worst case comparisons too. I mean, we want the worst case. See what it is. So let's find out. So let me try to wrap this up real quick. So basically what we're going to do is we're going to say, we're going to do a summation. I apologize for the small font here, but we're going to do a summation from 1 to h, which is the height of the tree, or at least the height of the parent of the tree. And we're going to sum a product. And the product is going to be the number of nodes at depth I minus 1. And I'm going to I minus 1 because h is the height. That means in a heap, the last parent is typically on the previous level. You follow what I'm saying? So number of nodes at depth I minus 1 times the number of comparisons per node at depth I minus 1. Okay? And I can see over here, so before I can set up my summation, so this is going to give me what I'm looking for. Before I can set up my summation, I have to say, this node is at depth 0, the number of nodes is 1, and the number of comparisons is 3 in this case. 1, 2, 3. That's the worst case, right? The number of nodes here are 2, but they're depth 1, number of comparisons is 2, because once you're here, you might go 1, 2. I understand this is only 1, but that's not the worst case. This could be also full tree, which also would require 2. And here I am at depth is equal to 2, 0, 1, 2. The number of comparisons in the worst case is 1. Number of comparisons, number of nodes here, maximum is going to be 8, and the number of comparisons is going to be 0. Those nodes are never going to be compared, actually, because they're only going to be looked at from their parent standpoint. So the number of nodes, notice it's increasing exponentially as a power of 2, so it's 2 to the I, right? And the number of comparisons is, what's going on with the comparisons? It is decreasing linearly. So our mathematical model looks like this. It's going to be 2 to the I minus 1, that's the exponential growth of the number of nodes, times Lg of n minus I. Does that make sense? So this is decreasing. Number of nodes is increasing, but the number of comparisons is decreasing. So that is 2 to the I minus 1 times Lg of n, and distributing this, minus 2 to the I times I, 2 to the I minus 1 times I. So you can see we're going to get some familiar looking summations. And so we have 2 to the I Lgn minus the sum of 2 to the I minus 1 times I, which is I 2 to the I. The Lgn is just a constant, because it's not a function of I, so it can come out. So we have the Lgn times, this is a geometric, and this is very close to I 2 to the I. So that can be solved by our telescope approach. So we have Lgn times this geometric series minus the sum of this one, which ends up being n. This is, by the way, Lgn 2 to the Lgn. What's 2 to the Lgn? That's n. So that's how we get n Lgn. Minus Lgn times this sum. And this sum is just, so I'm going to just show you how to do that. And then we get this one. So this is what we get. So now we can complete everything. So this is what the previous result was, minus this, and this is this. And so our full result shows us, when we combine it, all of this. So it's going to be this thing from the previous page, minus this summation, which is solved here, minus this, is going to be n. Okay? It's going to be n Lgn minus Lgn, minus n Lgn, minus n plus 1, simplifies to n minus Lgn minus 1. So our complexity, our theta complexity is theta n. So we can build a heap in linear time. So this is a very interesting analysis because it's a very powerful result. We can build a heap from a random array of data in linear time. That's even faster than, a lot faster than quicksort, but it's not the same thing. It's not, we didn't sort anything, but we know we can find the biggest element. How fast? In linear time. So let's say we found well, I'm running out of time, so I'm going to finish next time. All right, see you.